I'm going to talk about Omega, which is a new ocean model written using Kokkos. Omega is being developed as part of E3SM, which is the DOE Earth System model. What makes E3SM unique is we have a mission to use exascale computing to push the frontier of high-resolution simulation of the Earth system to answer pressing problems for the DOE. E3SM is made of multiple components, as sketched on the left. There are atmosphere, ocean, sea ice, river, and other models. And they're all coupled together. Each model is basically its own multi-physics application. The current ocean component that Omega aims to replace is called MPAS-Ocean. Those components have different computational costs. On the right, I'm showing a snapshot from our performance monitoring tool, where each box corresponds to a different component. Its height is the time spent in that component, and its width is the number of processors assigned to it. This is from a CPU simulation. So you can see that the atmosphere is the most costly, followed by the ocean. Since the atmosphere is already able to take advantage of exascale resources, now it's a priority for the project to do the same for the ocean. Doing so will enable high-resolution simulations of the ocean, and the main scientific benefit is that it enables us to resolve mesoscale ocean eddies, which requires resolutions of about 10 kilometers or below, and this removes some major source of uncertainty in the model, and this is just a pretty visualization of ocean eddies. Let me give you just a brief background of why we decided to move to C++ and use Kokkos. So we know that exascale means GPUs, but E3SM is a legacy, mostly Fortran code base, including MPAS-Ocean. CPU performance is still important for us. During the Exascale computing project, there was an attempt to port MPAS-Ocean to GPUs using OpenICC, but it ran into issues with the way the code is structured, and it did not bring the expected performance portability. The atmosphere model decided to port to C++ and use Kokkos, and that has been more successful. They were able to match Fortran performance on CPUs and obtain good performance on first NVIDIA, later AMD, and now transitioning to Intel GPUs with relative ease. So, and this culminated with E3SM winning the Goldenberg Prize for climate modeling for high-resolution atmosphere simulations. So given all of that, it seems natural to do the same for the ocean, and that's what we're doing. So the plan is to mostly directly port MPAS-Ocean, but we do plan to introduce some model physics changes. We have a large multi-lab development team with people from Los Alamos, Argonne, Oak Ridge, and Sandia. And of course, I'm presenting this on the behalf of the whole team. Omega development is divided into phases. Omega 0 is a multi-layer shallow water model. This phase is nearly done. Omega 1, the work on which has already started, will add vertical dynamics and ocean thermodynamics. Omega 2 will be the first version in E3SM, ready to be coupled. And Omega 3 will be the final release version with more physics targeted at 2027. As you can see, even in the project planning stage, we're moving away from Fortran as we started indexing at 0. Omega 0 solves the shallow water equations with using unstructured mesh. An example is shown here. This is mostly hexagonal with the finite volume method. And it's a multi-layer model, so above its horizontal serve, there is a number of vertical layers. The equations are shown here. They aren't super important. One thing I would like to highlight is that we have an option to run with arbitrary number of passive tracers, and I will use that to change my computational workload when I present performance results. Initial work on Omega focused on creating a framework for MPI domain decomposition, model configuration, parallel I/O, high-low exchanges, logging, timing, and testing. To say a few more words about testing, since we are doing some physics changes, we are not doing what is often done in our community, which is to do bit-for-bit testing. Instead, we are, of course, trying to write tests for every new feature, but we are also developing this tool called Polaris, which is able to set up identical test cases in MPAS-Ocean and Omega and produce some analysis. Usually, this requires a domain scientist to look at the output, but for some cases, we do have analytical solution, and here is an example of a convergence test. As we were developing the framework, we started experimenting with Kokkos. And the first thing that we did is to provide some simplified syntax for E3SM domain scientists, for multidimensional parallel loops, and introduce some type aliases. So we have this parallel for wrapper, which basically just hides the creation of a Kokkos policy. Now, logically, this should be an MD range policy, but we found out that it wasn't performing the best for our use case, so this implementation is actually a little bit more complicated. It uses just plain one-dimensional range policy, and then uses diffs and mods to get the multi-dimensional index. That's on GPUs. On CPUs, it's basically the same, except the innermost loop is kept serial. Another thing that we kind of spent some time designing is how we write the operators that enter the model equations. And we ended up with this functor approach where there is a functor corresponding to each term, which computes this term at one horizontal location, be it cell, edge, or vertex, and over a chunk of vertical levels. The chunk size is configurable, but it has to be a compile time constant. And this is mainly done for vectorization on GPUs. The chunk size is 1. Any static data, such as mesh connectivity or mesh geometry, is stored as member variables, and any dynamic data, such as ocean state, is passed as arguments. And I have here an example of the gradient of kinetic energy, the simplest possible term, where as member variables we have cellus on edge connectivity arrays and DC edge, which are basically edge lengths, and then the call operator computes this term for one index I edge over a chunk of vertical levels. And one motivation for this design was that we wanted to have flexibility to play around with kernel fusion. So if we now have two different terms, we can compute them in separate parallel forms, like shown here on the left. or we can easily transition to the code on the right, which does kernel fusion and computes them in one parallel 4. And now I would like to present some performance results and spend some time on this slide. This is quite busy. So first I'm showing single socket or single GPU or even single GCD tiles, TAC, whatever, results basically without any MPI. And as I mentioned previously, we have this option to run with different number of tracers. So first, let me focus on the plot on the left, which uses only 2 tracers. That's like a minimal ocean configuration because we always have temperature and salinity. And what this plotted here is model throughput normalized by thermal design power. This is like a naive measure of efficiency because I didn't have actual power measurements. And this is plotted as a function of mesh size. So in general, what we observe is on CPUs, the best performance is for smaller mesh sizes as expected because of caches, basically. Oh, sorry, I should go over the architectures that are shown here. So from the bottom, it's Sapphire Rapids CPUs on Aurora. And I use both DDR and HBM memory. So that's in magenta and cyan. Then in blue are Intel GPUs on Aurora. In red are MI250X on Frontier, and in black A100 on Perlmutter. Those 2 curves nearly overlap. And then in green, H100 on a testbed at Sandia. So for CPUs, the best performance is at low mesh, smaller mesh sizes. HBM just extends this performance region to larger meshes, but it doesn't change the peak performance. On most GPU platforms, we see this saturation effect with improving performance as we add more work until it's saturated, except on Intel GPUs, where there is a peak in performance at smaller meshes. And overall, we see about 2.5 to 5x efficiency gain on GPUs. And what was a little bit surprising to me that we see this efficiency gain even for the smallest mesh here, which only has 1,000 cells. Now moving to the right with 30 tracers, this changes a little bit because now we have enough work even for smaller meshes. So most architectures have peak performance for smaller meshes except MI250X, which is also still kind of monotonic, although much flatter. Okay, maybe in the interest of time, I will skip this and go to strong scaling results. So this is showing strong scaling from 1 to 128 nodes. This is for a mesh that's currently considered a high-resolution mesh for the CPU-Ocean model. Again, I have results with 2 tracers and 30 tracers. And what it's showing is wall clock time per time step, so now lower is better. We have results from Frontier on GPUs in red and from Aurora, both GPUs and CPUs, although CPUs are mostly there for reference. Aurora GPUs are in blue. And for 2 tracers, we see perfect scaling on CPUs, kind of expected that, and loss of scaling for GPUs at about 16 nodes, much more pronounced on Aurora than on Frontier. And I believe those two don't scale perfectly, but for different reasons. So on Frontier, I think it's just not enough work per GPU. But as we know from the previous result, that on Intel GPUs, we actually get better performance with smaller mesh sizes. So here, I believe the main reason that I have timers for that is the communication overhead that is much higher on Aurora. With 30 tracers, if we add more work, we scale better, so that's good. Now, finally, I see per node better results on Aurora as kind of expected because we have more GPUs per node. But there is already a hint of something going off for the highest node count that probably won't scale as good if I extend this plot. Okay, to conclude, Omega is a rewrite of MPAS-Ocean in C++. With Kokkos, it will be the future Ocean component of E3SM. We think we currently have, with Omega 0, good performance, portability, and efficiency on GPU platforms. And this is a nice baseline performance for future versions of Omega, which will include more complicated computational patterns. Okay, thank you.
All right. Okay, we have time for some questions. Christian?
The performance per TDP numbers. By the way, I really like what you do with plot, right? I think this is a way, how to actually compare platforms now, just because we are so architectural different, right? And it's really hard to judge. I think performance per dollar would also be great, right? But we don't have that information really, right? And it's all kind of meaningless anyway. So this is really good, really good. One question I had is, so with your TDP numbers and the PVC in this plot, how many did you just use, like 1/2 of the MI250X, or did you use both two MI250X, or is this?
So this was using only one GCD. Yeah, but okay. I kind of scaled it, like the full MI250X is 500 watts, I used 250 for my scaling.
Cool. Yeah, and the same for the PVC, is it used like one stack? I think I think we call it stack now. Yeah, we changed the name recently, didn't we?
Yeah, it's the same, but it's a bit higher TDP. It's 300, okay. I think.
I'm amazed, that you got these numbers and they look really nice.
Right. Mark, you have another question.
I know, I do.
You're loud, right?
So thank you for the talk. You mentioned that you had some performance issues with MG range policies.
Yes.
Could you elaborate a bit on those?
Could we elaborate? Our implementation sucks.
No.
Well, it's not the first report. The default thing that we do tiny is a bad idea.
Oh, yeah.
Can't pretend we've not done it much longer.
Okay. Is this a backend issue? Is it specific to the CUDA backend, like versus the OpenACC backend or whatever?
Most of them are bad.
Yeah, I think we got the best speed-ups for HIP.
Yeah, he said HIP is like the most impact.
And we know that there are a number of people who just use regular MPAS and use not because all the domain stuff. It's embarrassing.
Yeah, because I don't want to make people do dipmod on devices. The preferred way to do dipmod is to pre-compute on those.
We just need to fix it.
Okay.
All right, I think that brings us to the end of the session. So let's thank Maciej again and all the speakers in the session.